I think even within context learning, some of these works have shown that sometimes you run into cases where the data that you provide to a model in context conflicts with the information that it has been shown during pre-training, and then some kind of unexpected things can happen. Part of intelligence is coming up with these abstractions that, regardless of the environment, allow you to adapt, right, to the environment and be able to fulfill your fundamental desires. And those will depend on
any system that does retrieval. There still needs to be some kind of manifold or some sketch of a future situation, which we could then lean into.
To the degree that any intelligent system constantly learns from its environment and learns kind of what are the right abstractions to make good predictions in that environment, any intelligent machine has to do the same.
So the $1 million question is, how do you do retrieval taking into account the interactions between the data points?
This is actually quite straightforward. So what we do is
MLST is sponsored by SentML, which is the model serving platform for machine learning workloads. You log into their platform. The first thing you see is the SAS option. So this is the really simple option, just like on OpenAI. You can send requests up, you stick your access token in there, and you can access all of the latest open source models, and it's faster and it's cheaper. On Llama 405 billion, I was getting about 45 tokens a second. They quote 65 or so, but anyway, it's very fast and faster than the competitors. They also have PaaS options, which means platform as a service. Here's an example. So we're going to spin up an LLM inferencing service. These guys support OLlama and VLLM out of the box. So for example, when you've got the model up and running, you can use the OpenAI API, right? So you can use the Python SDK for OpenAI and you can use that to talk to your model. I was just using the cheapest option and I was getting very good performance on the new Llama 3.2 3 billion model. By the way, when you sign up, you get 10 free credits. Everyone gets 10 free credits, which means you can do some experimentation without spending a penny. Also, watch the interview I did with Gennady, their CEO, the other day. Enjoy.
Introduce yourself, and why are people going to love this episode? What are they going to learn?
Cool. So I am Jonas Hübotter. I am a PhD student at ETH Zurich in the Institute for Machine Learning, where I'm working with Andreas Krause on local learning and sequential decision making. So recently, I worked a lot on kind of making these ideas scale to state-of-the-art models. We work with large language models, and we're very excited to be able kind of to outperform some very large models on the PILE benchmark, which is this large, huge benchmark that comprises multiple kind of sources of language, from kind of language that you would find on the internet, on maybe Stack Exchange, Hacker News, to language that is used for math or coding. And we have been able to outperform the previous state of the art, which was a much more than 30 times larger model than the model we used, by spending additional compute at test time when you're faced with a certain problem. So what will go in today's episode is really kind of the idea of why can it be useful to spend this additional compute at test time. And the key aspect to this, which is really like fundamentally important, and without which this kind of learning at test time wouldn't work, which is how to automatically select the right data. So how can the LLM say what data it needs to make a good prediction? And so essentially, how can we use the LLM, the intuitions, the abstractions learned by the LLM, to decide how should it spend its compute at test time?
With the PILE, shout out to Aloytha. Yeah. I've got Nora Belrose coming on. I interviewed her at ICML. And of course, I know Connor and some of the folks there. But the PILE is interesting because you actually have the data, right? We don't have the data that OpenAI trained on.
Yes.
But I guess there's a couple of things. I mean, first of all, you could in principle still do retrieval against the PILE, even to augment, inference that you do on OpenAI. It shouldn't matter in principle that the distributions are completely different. But yeah, like maybe you can talk about that. So does it matter that the distribution of the retrieval data set is different?
I don't think it is, because so we evaluated on a bunch of different models, where on some models I know they didn't use the PILE as a training data set. For example, GPT-2, as you said, they didn't train on the PILE. I think the PILE was actually released after GPT-2 was trained. So GPT-2, it still works really well if we kind of augment GPT-2 by information from the pile. But at the same time, I think you can think of information in the pile as very kind of central in the data distribution that a lot of state-of-the-art LLMs are trained on, really, because these are very kind of academic data sets. A lot of these data sets are very kind of good in a sense. This is good data. So there's a lot of scientific publications, for example, and again, coding, math. These are things that today's LLMs are very much trained on. And I think what is quite remarkable to me is to see that these kind of this information that should be already very well encoded in this huge parametric model can still be useful if you show it a certain sliver, like a subpart, some very informative bit to it at test time.
The other thing I wanted to quickly comment on is I'm a big fan of machine teaching. So that was invented at Microsoft Research. And that is essentially an interactive form of transductive active fine-tuning. And it's mostly used for like classical models. But, the idea is that you have an application, and if you allow a supervisor to kind of like deliberately choose the most informative training examples, just like with dataset distillation, it's remarkable how much your sample efficiency goes up of your training set when you actually pick the most informative examples. But something like that could be used, I guess, with your approach, because rather than using the pile, why not just use Google search? So you could create an interactive workflow where the supervisor guides the search and selects the most informative examples. Maybe you could still run your like non-interactive version on top of that. And then you've got like a really informative transductive form of learning.
I think a very powerful paradigm that, I think you can still think about this in terms of kind of a kind of memory that you can access, but now where a certain piece of memory might not be static, but might be something that actually unrolls some underlying computation, right? Where the outcome is maybe not clear a priori, but which has a certain description. And we actually also in our group with a collaborator, Marco Bagatella, we worked on a setting like this, where your information gain is essentially not kind of pre-computable in the sense because the information is not static. Instead, you have to leverage your model's expectations of what might be the outcome of an experiment to say, okay, given that I expect this experiment to go kind of a certain way, how informative would that be for the task that I'm solving?
An extension question is, I'm interested in retrieval augmented generation. So I interviewed Patrick Lewis recently about that. And I could also imagine that this could improve retrieval augmented generation, but rather than doing like an in-context augmented version of RAG, you could do like a fine-tuned transductive active, like a transductive active fine-tuning version of it. Do you think that a version of that using your methodology could improve on RAG?
So I think, RAG is really this big ecosystem of various different methods that people have worked on. Certainly one of the big problems with RAG or some RAG systems is rooted precisely in the fact that they use this nearest neighbor search over some dense vectors embeddings. Often that's not exclusively what they do, but often that's kind of very core to what they do. And as we've discussed, this can be very limiting in the sense that it can select very redundant information. So empirically, it may very well be that selecting kind of most informative relative to some pretty useful metric of informativeness, selecting the most informative data can be better than just selecting the most similar data, which may be redundant. So that's one thing I would say. The other thing I would say is that the question of whether in context, whether you should put data in context or whether you should ingest kind of data via gradient steps is still a very open research question. There has been a bunch of different works that have kind of looked at the difference between the two. And it's not very clear yet in general which approach is most effective. What is quite interesting to me is that both approaches seem to be quite different in when they work and how they work. So for example, what was very interesting to us is when we worked with this pile data set, which again consisted of these multiple pieces of sub data sets, which related to multiple things that you could express in human language. What was very interesting to us is that with certain types of these data sets, fine-tuning was much more advantageous over in context learning than with others. And those tended to be this math data set that is part of the pile, DeepMind Math, which comprises school-level math questions like compute a derivative, solve this equation for X, those types of questions. But also coding or scientific papers from arXiv, or free law, which is a data set that comprises court opinions.
Yeah. So just addressing both of those things. So yeah, just with RAG, improving the retrieval mechanism. So doing some of the stuff you're speaking about, not selecting redundant information could improve RAG. And with RAG as well, sometimes just because of the architectural complexity, maybe you're doing retrieval from diverse data sources, and maybe there's some subsequent step to, again, remove the redundant information or re-rank them or do something like that. I'm not sure whether existing systems do that. But then there's the question of like in-context learning versus fine-tuning. And there must be some interesting kind of trade-off there, because I've always thought that in-context learning is better because just anecdotally, the precision seems better. Like if there's something in your context, it doesn't seem to hallucinate. Where I have this intuition that when it's inside the model, the information is lower resolution because it gets entangled and expressed as part of like the low level representations in the model. That might confer some advantages because the model can use more of its base knowledge to reason about the thing that you're doing, but disadvantages in the sense that it's more likely to hallucinate about the thing that you're talking about.
There has been a bunch of works that's also just related to trying to understand how in-context learning works. I think even within context learning, some of these works have shown that sometimes you run into cases where the data that you provide to a model in context conflicts with the information that it has been shown during pre-training, and then some kind of unexpected things can happen. Generally, I agree that the data that you put into context with these LLMs that we train today, the next token distribution is very heavily skewed by that. And so your model is much more likely to refer to some specific piece of information that is in context versus some specific piece of information it has been trained on. On the other hand, though, backpropagation and kind of gradient descent are very effective methods. It seems so, at least they work during pre-training. It seems that they are very effective methods to teach a model how to reproduce a certain pattern. And of course, there's this argument kind of the connection is that if you do that long enough, if you scale that up enough, you will have to develop some abstract forms of understanding, because to be able to kind of predict the next token given previous tokens, you have to maybe learn abstract learning algorithms and so on. So for example, if you're faced with a math question, and now you're doing backprop over this example that computes the derivative of a certain term, then to be able essentially what backprop will teach the model is how to reproduce this. And if it teaches that on multiple of these examples, arguably the model will find some form of reproducing that behavior. Whether that is the algorithm that we want or not, that's a bit of a different question, but it will try to imitate it to some degree.
I love thinking about purpose at different levels of description. We were talking about this on our Patreon call last night. Keith Duggar gave the example of an anthill. So it has a purpose, right? And it programs all of the little ants, and the ants can adopt different roles. And it's very, very simplistic. They smell pheromones or something, and sometimes they'll go in the path when they find food. They'll like drop the pheromones. Sometimes they don't, and that means other ants will follow the trail, and then the trail gets reinforced and so on. And even though the ant is just following these very, very simple rules, it serves the purpose of the anthill. But then there's the question of, well, it doesn't have an intrinsic purpose. The purpose is something we ascribe to it.
Maybe. It makes you certainly think, if you talk about kind of these simulated games that simulate humans in their life, to what degree we have like more purpose than the ants, because certainly like some of these city builder games, they get pretty close. Not perfectly accurate, but pretty close to how humans move around in the city. And there's certainly kind of a lot of societal inflicted purpose that makes us go around, like be it go to school, be it go to work, be it go to like a restaurant or to a grocery store to get food. And those are like fundamental needs that either like come directly from being a human or just from society. And certainly a lot of the purpose that is driving us around is not necessarily intrinsic in that sense, and is like externally comes from external forces. But
Yeah, it really does. How much of it is internal, though?
I don't think, like, I don't have the kind of background to be able to actually answer that question. I think, I mean, probably because, I mean, the city build, like staying with the city builder kind of metaphor, I don't think they in any way, shape or form represent truly internal motivation, right? So you can already say like anything that is kind of not in the gap between these simulators of cities and what you observe in the city, anything that is kind of not inside that small gap cannot be internal, right? Because that's somehow external or from society or from kind of a byproduct of the larger simulation. And then there's only a small sliver remaining, right? Of course, I think the human, like part of the human constitution is much more than how we move around in the city, right? And there's a lot of stuff that's happening in our brains, which is not covered by that, but yeah.
I mean, this came up with Eliezer Yudkowsky and Stephen Wolfram the other day, because they were talking about where do wants come from? You know, you have an intelligent system, and you can model it as a thing that has a planning horizon, and the bigger the horizon, the more intelligence, the more agency it has. And then, okay, well, why would he argue for something like instrumental convergence? You know, that when you have a super intelligent AI system, that it will have predictably bad intermediate or instrumental sub-goals. And you can think of it just in this city setting that you were just talking about, that all of these different agents, there are constraints. It's a bit like they have to follow through certain rivers, or in the case of a city, they have to go through certain roads. They have to, in order to transact with each other, they have to use money, and they have to do all of these different things. So it kind of like canalizes or truncates the space of future behavior. And it's not just physical extrinsic constraints, it's also kind of like interactions with the behavior space of other agents in the future.
Yeah, I think like my view that a large part of this is abstraction. So as you kind of give I think a lot of these systems, even like these artificial systems that we kind of give today, they do have some kind of extrinsic goal that we ascribe to it, be it either like just to imitate the distribution of things that we give to it, or like some explicitly formulated goal. And then I think the kind of wow moments that the AI community has accumulated over the years, to a large part, are situations where, leaving that goal aside, the agent, if you want to call it an agent, came up kind of with some sub-goal that was actually the result of kind of an abstraction. Like the agent was kind of abstracting from the immediate goal. It wasn't kind of greedily trying to solve that goal. It kind of came up with this abstraction that allowed it to kind of take this intermediate step, which maybe wasn't obvious to a human, to then still with the purpose of solving that goal, which was obvious to the human. And I don't know. I think it's definitely interesting in the sense, an interesting question whether coming up kind of with these intermediate goals or intrinsic goals, as you might kind of say, is purely a function of being able to abstract, or if there's something else going on. I tend to err to the side that this is really purely the power of abstraction. But yeah, I don't have all the answers there.
Yeah, well, Schmidt-Huber said that intelligence is compression, by which he meant abstraction. But something I think about as well is that, again, we were talking about this last night. The reason why, asynchronous distributed software systems are so exciting is because that's how the natural biological world works, right? And if you use an extreme example, like if we had some space station, 30 light years away or something like that, like you have to get a message to it. You have to have a topology which has a kind of locality prior, right? So that's the way biological systems work, right? The cells send messages to each other, and it all just kind of emanates out in this asynchronous way. You kind of send messages. But when we design AI systems, it's kind of different. They don't emerge. They're not grown. Do you know what I mean? They learn using stochastic gradient descent. So at some point when we build AI systems, we have to design them. We actually have to put in information boundaries. And we need to say that, like you are talking to this at this level of abstraction. And that seems completely divorced to how things work.
This, I don't know if I fully agree with. in some sense, I mean, I agree with the kind of framing that we design AI systems and we kind of put some boundaries in place, like what is the amount of compute you get, what is the amount of memory you get, in some sense, what is the amount of data that you will see, but I think we're going beyond that. So you can certainly think about these systems that are following these fundamental principles, whether that is some form of gradient descent or some other learning mechanism that is human engineered, to, in the end, interact with the world and maybe design their own experiments to then be able to actually decide themselves what type of data I accrue from my environment. And in some sense, how I kind of move into space and how I kind of, in what direction I evolve kind of my kind of compressed representations.
Well, let's talk about this kind of behavioral plasticity that you're talking about. So, what I love about active inference is that there are no explicit goals. There's no explicit reward function. In fact, you can think of it as a form of maximum entropy inverse reinforcement learning, where it actually starts with the statistical distribution of the data, and then it kind of infers within constraints what the reward might be. And I really like that, because I kind of feel that we need to have systems that can kind of like materialize their own goal, rather than us as designers kind of saying, you need to do this thing.
I think on a different level of abstraction, that is still a goal that is human engineered, right? We still, as you said, we still design the AI system and design the learning mechanism, like even, the various forms of active inference, how it materializes in practice, because you have to come up in that case with like some probabilistic model over which you can kind of optimize the expected free energy. So I think in the end, it's still, even kind of that form on an abstract level, you can think about as some form of human engineered. I don't like the term reward because it's like so linked to this reinforcement learning community, but kind of a similar thing. And then I think really the argument that people make is that, of course, that will lead to different emergent behavior than if you gave it a different reward, like something that is more commonly done in reinforcement learning, where let's say you are working with an Atari game and you just give the game score. And of course, also in reinforcement learning, if you give an agent a different reward, the agent will kind of start learning differently. And again, going back to kind of what we discussed earlier with kind of intermediate kind of sub-goals being actually a function of the abstractions or kind of byproduct of the amount of compression that the agent was able to achieve of kind of its information, then I think to that degree, both ways can and will probably find these intermediate sub-goals that we as humans would find interesting behavior. And I think that is to a large part what, in my view, people in active inference are kind of hoping for, that if you scale these probabilistic models up, then a byproduct of maximizing this expected free energy will be these interesting behaviors that lead to, kind of self-sustaining organisms and that kind of stuff.
Yeah. I agree with what you've said, though. Like, even with active inference, I think part of its selling point is that it's kind of human, parasitic, in the sense that when you build the systems, it will have agency in a constrained way with preferences that are compatible with ours. And that's fine. But don't we want to have AI systems with more plasticity, right? And I think what you say is true, right? We design all of these inductive priors. We constrain the systems in such a way that they will behave in an anthropomorphic way. But I guess you can make the same argument about DNA. So DNA has this insane, some people might say it has a kind of constraining force on our behavior, but it doesn't seem to do that, right? If you look at our society, like the way we construct language with all this beautiful diversity all over the place, but so there's this asymmetry that even though like it's all based on DNA, like if we deleted all of the DNA, like we would all be gone tomorrow, but it allows this complete fan out of behavioral complexity, but still constrained in some way.
I think this is very compatible with the view that, in the end, I think the DNA in our form of life gives us some very hard constraints, right? We have to consume water, we have to consume food, right, to survive. But within that, there's quite a lot of kind of pathways to achieve that. And they are also very dependent on the society around us, right? So that's, and not just the society, our environment, right? And that's, I think, part of intelligence is coming up with these abstractions that, regardless of the environment, allow you to adapt, right, to these kind of to the environment and be able to fulfill your fundamental desires. And those will depend on the environment. And in case of humans, because arguably we have kind of some non-trivial amount of intelligence between humans, how we kind of achieve our goals is also different. But I think this is really a spectrum across all animals. And you can see now that kind of the animals, now with climate change, the animals that are very kind of attuned to their environment, while they can kind of cope with small changes in their environment and kind of adapt to those drastic changes in the environment, their learned abstractions, if you will, are useless, right? And then they cannot survive anymore. So yeah, I think.
Where do the abstractions come from? What kind of abstractions do we hard code into the architectures, and what kind of abstractions are meta-learned?
I think this is a fundamental question, I think, that has been at the core of machine learning, and even more so AI since kind of the inception. And I mean, a lot of people, they started with kind of hand coding these abstractions, right? In a sense, leveraging human learned abstractions, or it was what we deem to be useful abstractions, but fundamentally being limited by this language of, or kind of by the language of how we can express these abstractions, and also by our finite time, right? And then I mean, neural networks went beyond that and learned these abstractions end to end.
Are you a fan of Chollet's kind of type 1, type 2 dichotomy?
Generally, I try to not use kind of this kind of system 1, system 2 dichotomy, and also kind of the word reasoning that is somehow linked to system 2 sometimes, because I don't find it always so kind of informative. It's definitely like a loaded term that is kind of very differently interpreted in various communities. I think my hunch is, but I might very well be very wrong about this, is that really kind of this more, if you will, planning behavior can emerge from learned abstractions. So as we kind of go up layers of abstraction, if we do make predictions on a very high level of abstraction that may seem like something kind of planning, more intelligent is going on. So maybe this system 1, system 2 thing is just kind of a question of what level of abstraction we're operating on. And certainly going up levels of abstraction requires more energy, more time, and is computationally harder, strictly harder than doing this more shallow kind of finding these shallow abstractions. So in that sense, I think, kind of I resonate with that idea, but I think there are various different interpretations, right? That different communities have come up with of how actually the system 1 versus system 2 should be materialized. And I don't find myself necessarily in all of those.
Very cool. Why does fine-tuning a model, let's say on a batch of examples, cost less than doing inference within context learning?
It's because the information gets compressed into the weights.
Mm-hmm.
And in context learning has this problem that for every new token that you generate, you have to attend to all previous tokens, right? And that essentially, you also have to go once over all previous tokens. And that is...
But I guess I'm just trying to understand fundamentally, why does the backward pass not be symmetric with the forward pass from a computational point of view?
I think the key is here that it's really amortized in the weights. So in context learning kind of has to present all evidence at once. Otherwise it doesn't work because there's no amortization going on. So in that sense, it's really like a full working memory. Every kind of bit of information is accessible at once and you have to filter it out at once.
Oh, I see. So when you do the fine tuning, I mean, obviously there's a batch size.
Yeah, there's a batch size, right? So,
you know,
I mean, that we essentially pack it into multiple, boxes, like multiple sequences of tokens, and separate them, and then present them kind of one by one.
I got it. So it's still quadratic, but it amortizes to linear because it's so small.
Yeah, yeah, exactly. And you have to, I mean, really, that's the key, and that's why we train parametric models in the first place.
Yeah.
Because we try to amortize the data, right? We try to compress the data, as opposed to give all the data at once, which you could also do with a non-parametric model.
Yes, because I suppose with something like a kernel function or something like that, you would need to have all the data.
Exactly. That is kind of the first ideas of local learning are in that direction, right? I mean, it's actually the trajectory of local learning is quite fascinating to me because it's quite a linear trajectory, kind of working with these separate components. So actually, like in the 50s, people came up with nearest neighbor retrieval, where you have like this distance function, and then you just average, kind of to get a prediction of a new point, you average the predictions of all the points around it. And then people came up with kernel regression in the 60s, which is essentially doing the same thing, but now you're weighting the importance of the points relative to their distance or relative to some similarity measure, which people call the kernel often.
Yes.
And
Vladimir Vapnik.
Yeah, exactly.
Yeah.
And then from there on, people went into different routes. Like there was more development of the non-parametric side. People then in the 70s, they started to do locally weighted linear regression. So where they would train a separate linear regression head for every prediction that they make, and then locally weight the training data around the prediction. So ascribe higher weight, again, based on some kernel function, higher weight to the data that is around the point where you want to make the prediction, and less weight away from it. But that kind of adds this parametric component, which I think is key to this framework.
There's always been this kind of, juxtaposition between inductive learning, right, which is when we learn a general decision function which could work for any new piece of data, and transductive learning, which is particular to particular. So this is when we learn a statistical function for a given input. And this is quite a new idea to a lot of people, but actually, as you're saying, this has been spoken about for decades by people like Vladimir Vapnik.
Before this kind of revolution of deep learning took off, so this idea has been definitely around since the 70s at least, but kind of early indications already before with people doing this nearest neighbor search in non-parametric models. Yeah.
Yes.
There's kind of the spectrum. I like to think about this as a spectrum where in some problem domain, let's say it's natural language, you try to fit kind of some like data manifold that describes some aspect of natural language that you care about. And this inductive paradigm is all about fitting all of that at once. So you extract some general rules that hopefully generalize to describing accurately your kind of function that you want to learn about over this entire manifold. And that is still in some way, goal directed in the sense that you are limited by what is expressible in your problem domain that you work with. And traditionally, people have worked with rather small problem domains, right? So you start with MNIST, like recognizing handwritten digits, and then you quickly realize, okay, it's a fairly narrow kind of amount, like small amounts of information that you need to extract to do this prediction, right? Because you're working on a very small problem space. But nowadays, we're scaling this problem space to natural language and beyond, images, video, really a huge problem space where a lot of hard computational challenges can be expressed in these formats that we are learning over. And this paradigm has roughly stayed the same, where you still kind of try to learn one function that amortizes everything, right? So you kind of learn kind of amortized intuitions about how your data manifold looks everywhere. And then when you do inference, when you do a forward pass, when you make a prediction, you use a fixed amount of compute cost to access kind of your amortized intuitions of how your function should look everywhere. But of course, in practice, there are certain parts on the data manifold that will be very easy to predict and easy to learn. And there are other parts of the data manifold that are very hard. And on these kind of more complex problem domains, this is very evident. In human language, there are simple tasks like, that's what humans do when they go on autopilot. We talk about the weather, right? Like you have like these small chats where you talk about random stuff. But then you can also go deeper, and that's where humans need to think, right? That's when we also spend kind of more of our kind of brain's computation to be able to solve these problems, or even attempt to solve these problems. And that is not really captured by this inductive paradigm.
When I learned about machine learning, it was in the days when, I guess it was the second AI winter. So it was like support vector machines and kernel methods and stuff like that. And I learned about conformal prediction, and I learned about transductive inference because Vladimir Vapnik was at my university. And it's a little bit like, do you remember in the 1980s, we used to have to do these insane optimizations with memory because we just didn't have things that worked very well. So we were leaning into the optimization back then. And I guess now we've been in a regime because of the deep learning revolution that we felt that we haven't needed to do it because the deep learning models work so well, apparently even in the multimodal high scale setting. They just seem to work very well. And it's almost like people have started to delude themselves that these aren't even statistical models anymore. And why would we need to do any kind of like local optimization? So that's very interesting. The other interesting thing that you said is I think humans do this as well, that when we deal with situations that are unpredictable and full of ambiguity, we do more processing. I interviewed Professor Mark Solms, and he's like a neuroscientist, kind of, what's the best way to describe him? Anyway, let's just say neuroscientist. And he says that consciousness is something that, that we become conscious of situations when we are faced with ambiguity. And it's counterintuitive because when you're outside sitting in the sun and you're very mindful, you think of that as being like your brain is doing less processing, but you can kind of interpret it actually as you start noticing the clouds and the trees. Your brain is actually like processing more information, not less information. So having like a variable amount of computation that we perform in like sensing more information, processing more information is a very interesting thing.
I mean, it's certainly fascinating with the human brain where not my expertise lies for sure. It's the case that there's a certain amount of energy, right, that we can turn over to kind of do processing in our brain at a given time. So we cannot do everything at once, right? It's impossible. So we have to be strategic of how we use that energy to achieve our goals. And I think fundamentally the same is true with machines.
Yeah. Which brings me to the next thing. So the other day we came up with this really cool analogy to describe the behavior of I suppose, machine learning models. And it's like Google Earth. So in Google Earth, you have this variable resolution. So you start off up here and you have big coarse tiles, and then you zoom into London or to Zurich and the tiles get smaller and smaller. And it's a great locality method which allows you to kind of like use the compute where you need to use it. Is that a good analogy for the kind of work you're doing?
Yeah, I love that analogy. I think it captures really the essence, where you can think about kind of the number of pixels you have as a given kind of representational power, or maybe compute power that you have at a moment to represent something, to make a certain prediction. And kind of in this inductive paradigm where you want to represent the picture of the entire world at once, there's only so much resolution that you can afford to spend on any individual kind of prediction, let's say of like the city of Zurich or something. So that will maybe be a single pixel, if not even. And the power that you get if you zoom in kind of is evident to anyone who has ever used Google Maps. If you were to kind of zoom in by just making the pixels larger, kind of not changing how you use your resolution to represent the local information, if you were to just make the pixels larger as they are, pretty quickly Google Maps would be completely unusable, right? And that's actually super powerful. So if you let's say work on a computer with like 1980p display, and you have like your friend who has a 4K display, but has not figured out that you can actually zoom by reallocating the compute that each pixel does, but just thinks you can only zoom by making the pixels larger or getting closer to the display, right? Then you can pretty quickly outsmart him, right? While he maybe initially has a little bit of an advantage because he can represent more information at once, you can, if you want to go, a little bit deeper, want to look at kind of Zurich, from space, then you have much higher resolution already than he does, because you're just using your representational capacity, or you're using your compute in a smarter way.
Yeah, so this is one of the reasons why I've been fascinated by this concept of active inference. So, Carl Friston is one of my heroes, and he's got this wonderful model of agency. And I guess the stark difference between an active inference agent and a lot of, traditional machine learning is that it's actually doing kind of situational computation. Right. And that seems so incredibly important to me. And I feel that you're introducing that, but in a slightly more internalist way. Okay, can you explain what I mean by that?
Sure. So the recent work that we have done is all about kind of locally zooming into the distribution that language models learn. So locally kind of learning that data manifold better. And the way it works is that you have you stay with your kind of normal language model that you're working with, kind of fixed parametric model. And then on top, at test time, you can look back into your memory or big data set and find examples that describe how that manifold looks locally around the prediction that you're trying to make. And then just refresh your memory, right? Spend a little bit of additional compute to kind of use your representational capacity specifically for the prediction that you're trying to make. So instead of trying to kind of still all at once learn the entire data manifold, now we're in the game of just kind of making predictions specifically targeted to a certain task that we're faced with at a time. And it's really about kind of using compute and using representational capacity to its fullest to make a certain prediction.
So there's a beautiful figure, I think it's figure 2 in your SIFT paper, and we'll kind of like talk about that a little bit as we go. But you've got the data space. Okay, so the data space, I guess, is like the Euclidean space of the selected data, and then you've got the data manifold. So the data manifold is this kind of surface or this structure which is actually learned from the data, and then you do, let's say you have an example that comes in, and you want to do a really good prediction for that example. So it kind of seems logical that you should go and sample a bunch of the information in the neighborhood of that sample, because that will improve the statistical power of your model. Now, there's a few things here. So I guess the first question is, where do you get that data from? I'm guessing you use something like, there's FACE, and there's like a whole bunch of things for doing like a nearest neighbor, kind of lookup, and they might do vector quantization or some kind of like, log retrieval time method. And then inside that, you do an improved search as well. But maybe we'll start with what's the difference between, like, you could have a really, really big base model, and there's a ratio between how big the base model is and the cone of your selection when you do information retrieval. What's the relationship between those two things?
So I think what you're alluding to the fact is that with larger base models, we are able to capture the data manifold in a better way. So even if these larger base models try to essentially make all predictions at once or amortize these predictions so that we can essentially access them at constant cost when we do inference, larger models mean we get kind of better representation, more representational capacity, and we can learn the statistics better, essentially. And what we kind of are showing is that this local learning at test time is an additional mechanism on top that, regardless of what kind of representational capacity you start with your base model, if you add that on top, you just kind of get that additional kind of extra bit of representational power to make a better prediction. Essentially using your kind of representational capacity to its fullest when you make that prediction, right? Because at any point in time, your pre-trained language model, if you will, has to encode all of this information, right? Because it has to solve a lot of different tasks at once. And now when you're tasked with making a certain prediction, usually it can just, forget. It can ignore most of the information that it has compressed. And that means it can represent the pieces of information that are critical to actually making good prediction at higher fidelity, right? So you can make then also a prediction at higher fidelity.
So I'm thinking we're kind of assuming that there's one data manifold, one data space. why not partition it up? So instead of having a multimodal embedding space, let's say we've got something that can do text and images and video. Why not separate it out and have different modalities, different data spaces?
Yeah. In what sense do you think that might help? Are you meaning one could train like a separate model for each of them, and then for kind of you split your data manifold into multiple submanifolds and then just train a separate model on each of them and then be done with it?
I think so. I think like one of the things we're playing around here with is we're in this regime at the moment of having a single model which is trained on every data modality. And your work is hinting that specificity helps a lot, or having a local situational method helps a lot. But couldn't you say the same for even the modality of the data? I mean, couldn't you just keep partitioning and create some hybrid system? And would that give you more or less statistical power?
So I think we have to separate a few things here. So the first thing is, of course, if you are kind of making a certain prediction in some specific modality, being able to really focus on that modality is useful. But of course, if there is, let's say, information, or if your kind of entire data manifold that is not kind of cut into its subparts contains information that is necessary to make a good prediction, but it's kind of accessible only in a different modality, then you need to have this cross modality to be able to access that information. So there's really two key elements here. There's the first key element is to be able to use the entire representational capacity to make a certain prediction and kind of overfit to the test problem at hand. But the other key aspect is that we need to have the right abstractions, or we need to have learned the right representations to be able to decide what data is actually useful, what data contains the necessary information to make a good prediction, and also the right abstractions or the right kind of learning algorithms to turn this information into a good prediction. And generally what we have seen over the last couple of years is that if you scale these kind of deep learning models up, and if you show them a wide variety of data kind of during pre-training, then they get better at kind of finding these similar patterns across modalities and also across problems to kind of come up with more solution algorithms or kind of simple mechanisms that allow them to kind of synthesize things. So for example, if you ask ChatGPT to write you a song about a certain topic in a certain style, it will do that. But that's certainly not possible if you have never shown it, any examples of songs in its training data. So I think this cross modality is really key, and that doesn't necessarily detract from the fact that you want to, at test time, use your representational power to, after having seen a little bit of everything and understanding how kind of everything behaves, to then focus on those things that, given your abstractions and your knowledge, you think are important to make a prediction.
So I think we should contrast your work to active learning. So I guess in the olden days of machine learning, we would produce a decision function, and we would have a test train split, or maybe a validation split, and so on. And then active learning came along, and active learning said, well, actually, you might be faced with a shifting data distribution. So when this thing is used next week, the distribution might be different. So why don't we continuously retrain the model on the shifting data distribution, and active learning would select, let's say, sort of diverse and new training examples. But what you're doing is a type of active learning, but it's deliberately honing in on the specific rather than looking at the general.
Exactly. So I think you have put it very well. I would kind of extend the characterization of active learning a little bit, in the sense that a lot of active learning has just focused on how can we kind of sub-select the training data that we use in the standard kind of pre-training and then evaluation paradigm, so that we can use less data, but kind of compress already the information that is contained in the data in such a way that the model will still be as powerful as if we had trained on the entire data. And people have shown in some cases that can be useful and powerful. But that in those cases, random is a really strong baseline, and random has often, outperformed a lot of these methods. Now, what I am working on is a very kind of different but similar in some ways setting. The setting that I'm interested in is local learning. So making these specific predictions. And in that case, there's only some kind of small sliver of the entire information that is kind of in your memory that's actually relevant to making that prediction. And actually searching for that is a key aspect, but you also want to maintain diversity in the information that you obtain. So actually the methods that we end up working with are some kind of mixture between methods that people have looked at traditionally in the kind of literature on search and the methods that people have looked at in the literature on active learning, which are all about kind of finding diverse samples.
Very cool. So we're kind of blending information retrieval and active learning in a very kind of like specific way. So maybe we should start with the search. So you said in your paper very beautifully that the naive way to do this is I have an input example and I have a training data set or something like that, and I should just go and retrieve the nearest neighbors, again, using some kind of like vector quantization retrieval system like FACE. So I could retrieve a whole bunch of the nearest neighbors for this input example, fine tune my model on those nearest neighbors. What could possibly go wrong?
There are a lot of things that can go wrong. And the main thing is that nearest neighbor has really been designed as a search method. So if you have like a big bag of possible kind of solution candidates that you're looking for, like a needle in a haystack problem, it tries to give you kind of as many candidates that match as closely as possible to your description as you want. What you realize is in local learning, you actually want to learn something, and learning something requires synthesizing different pieces of information. So for example, if your task is not a simple retrieval task in the sense that the information is exactly encoded in your data, and you just have to find this one piece of information and then return it to the user, when instead there's a lot of different pieces of information that are kind of disseminated in your data, and you need to find all of the relevant pieces and kind of return it to the learning algorithm at once. Then nearest neighbor will not work, because nearest neighbor kind of just focus on the dominant frequency or kind of the most similar aspect that kind of some subcluster in your data has to whatever you are asking it about. So for example, if you give kind of your engine a question, we had this example with where someone was asking about the age of Michael Jordan and how many kids he has.
Yes.
Essentially, kind of the data in your memory you can think about as just representing some clusters. So some part of the data is just information about his age, and some part of the data is just about his kids. And in practice, what happens is in this kind of latent abstraction space, just one of the classes will be closer to your question that combines both. And then your kind of nearest neighbor search will return all pieces of information that are about one of the topics. I think in that case, it was the age first, before it ever finds any of the pieces of information that are about the number of kids.
Yeah, so we'll show this figure on the screen, but the prompt was, what's the age of Michael Jordan and how many kids does he have? And the nearest neighbor approach basically doesn't even address the number of kids that he has, because it almost like it latches on to the first. We did this
experiment actually, and this was we did it in a very simple setup where there was really just 4 pieces of information in the memory. 2 were about his age, 2 were about the number of kids he has, and we just requested kind of the closest 2, and normal nearest neighbor will just repeat redundant information, because there's nothing stopping. Like there's nothing in the objective of nearest neighbor that's actually quantifying how informative the set of examples should be that are returned. It's just caring about really the marginal closeness, proximity to what you asked about.
Okay, so this is really interesting. So the way we do the information retrieval is using like a bunch of embeddings. And I think in your paper you said you're using Roberta embeddings, and that may or may not be relevant. But you're saying, rather than just searching using some similarity metric in Euclidean space and getting the nearest neighbors, we should have the concept of information gain with respect to some task. So in this particular case, the task is, I need to know this and I need to know that. And we're saying, retrieve me the examples that actually give me the most information for that thing that I want to do.
Exactly. And the funny thing is, if you just try to retrieve one piece of information from your data store, those two kind of views turn out to be pretty much equivalent, right? Because if you can only access one piece of information from your memory, the best thing that you can do, kind of your best shot, is to just take the thing that is most relevant. But as soon as you have picked that kind of piece of memory, and now you're looking for the next piece of memory, just finding something that is as close as possible or as related as possible to what kind of your task is not the best thing anymore, because that might be exactly the same thing that you've already seen, right? In case there's literal exact duplication in your data. So instead, what you should do is to both look at how relevant a new piece of information is, but also how non-redundant it is relative to the piece of information you have already assembled. So you are essentially trying to solve some trade-off between finding examples that are as related as possible to your prediction and finding examples that are kind of a diverse representation of all the information that is encoded in your memory.
That makes sense. So devil's advocate, you're saying that we do some retrieval around a cone, and if the cone is very small, so if the specificity is high, nearest neighbors will just produce a load of redundant information, and it will miss a lot of it. It won't be sensitive enough to capture all of the information in the prompt. But what if we just increase the cone? So what if we select nearest neighbors, but we select, let's say, 2,000 nearest neighbors or something like that? So then, yeah, we've got to fine tune on 2,000 examples now instead of 5. But probably some of those examples would have information about how many kids that Michael Jordan had.
That is definitely a fair point. And I would say that really there are multiple things to say here. One is it is actually not just important what you see, it's also important how you see it. And it turns out that it's actually, it is sometimes useful to see the same piece of information repeated, but it depends on really that piece of information and your learning system, how good your learning system is, how strong your learning system is. So, for example, if you like, let's say you work kind of with some math questions and you're faced like with a problem where you have to compute the derivative of some equation, and then you look into your memory and look into similar problems that you have solved before. Now, maybe there's a cluster of a lot of other kind of problems that were about finding derivatives, but all of them used kind of some trick to find the derivative that is not applicable here. And now you will just train on them a lot and you will overfit to them a lot. So it turns out to be very important to be careful with how many gradient steps you do on a certain example. And it turns out that the kind of solution method that we propose, which is called SIFT, takes care of that explicitly. We have this one figure in the paper, which I think is quite insightful in that regard, where we actually look at all the examples where SIFT decides to just fine-tune on the nearest neighbor repeatedly for 50 steps. Right? Because there's no notion in SIFT that all pieces of information have to be separate, like in nearest neighbor. So SIFT is perfectly fine with just fine-tuning on the same piece of information if it is helpful. And in all those cases, it is drastically better than nearest neighbor, right? Because nearest neighbor would just explicitly take this piece of information once and then move on to other parts, even though they might be less insightful. So I think there's really a spectrum. And as you said, it might be good to train on some examples a lot, but nearest neighbor is kind of this heuristic that doesn't take this question into account, whether it's actually good to train on examples more or less.
So another thought that occurs is, I guess, representation bias, and also the robustness of models to fine tuning. I remember I read in Francois Chollet's Deep Learning with Python book. He basically said you've got to be careful with fine tuning because these things, fine tuning can quickly overwhelm a model. And if you turn the learning rate up too high, for example, or you do too many gradient steps, it's almost like you, at some point, the model kind of forgets everything it knew about previously, and it leans too much into your examples, and that can cause overfitting. And the representation bias might be, actually, it kind of like you almost don't want it to be overweighted by the thing you're retrieving. So is there some trade-off there?
There is some trade-off there, and of course, if you were to use a very high learning rate, your kind of locally fine-tuned model will not work well anymore. I think it's really a very natural thing. So what you want is you want to somehow take kind of this local information and kind of use these examples as a way to kind of show your model it's fine to kind of forget some information and fit this new information more closely. But in a similar vein, you don't want to just encode this information and then, I mean, if you do a lot of fine-tuning steps, eventually it will just literally memorize this specific or just try to predict the specifics that you retrieve from your memory. So there is some trade-off and you want to be somewhere in between. That's what I would say.
Yes. Yeah.
I think one of the key things that came out of our work, and this is part to how we actually do the information retrieval, if you want to frame it that way, is that you need to kind of get a hold of the uncertainty of the model. So, and that's really a key aspect. And the uncertainty tells you how, kind of based on the current model's representations, how would the model change, or how more certain would the model be if you gave it a new piece of information? And now you can use that to say, okay, this piece of information is very relevant to the prediction. It's very informative. It's kind of needed to make a good prediction. Then I'll show it to the model. And at the same time, maybe there are some pieces of information that are not relevant to making a good prediction, and then you can exclude them. And so you can, in some capacity, determine for a given example, if you have important information in your memory, in that case, you should use it. Whereas if you don't have relevant information in your memory, then you should not do fine-tuning at all, maybe, or not as much.
And how does the embedding function affect the results?
So the embeddings are crucial, right? So the embeddings, in a sense, describe this data manifold. So the embeddings describe really essentially how informative a certain piece of information is to something else. And this is really closely linked to this linear representation hypothesis that is widely studied, especially in interpretability. And essentially, this linear representation hypothesis says that kind of abstract concepts with complex enough neural networks, LLMs, are represented as kind of linear directions in some representation space. And that representation space is accessible, so we can tap into that. Now, you can think about kind of these representations as describing the data manifold. So things, kind of concepts that are very aligned in that latent space are very relevant to one another. So if you want to make kind of a smart statement about one of these concepts, you better know about this other concept that is very closely related to it. And in a sense, if your abstractions are not good, then you will not identify these related concepts. Just concepts that are to us seem very related, that we know are very related, the machine will not have identified as related, and then it's useless. And that is kind of part of the story why 20 years ago, when the representations were not as good, people did not talk about the linear representation hypothesis, because machines were not yet able to actually identify these concepts, which we as humans know are related.
Yeah, Neil Nanda was telling me about this when I spoke with him last time. He's an amazing guy in MechInterp. And yeah, so this idea essentially, I mean, we've been speaking about a manifold, but concepts and so on can be thought of as having some linear direction in space. And there are examples of using linear probes. There was that Othello board game example where you use a linear probe and you can kind of like extract board state and so on. But also, I think it's useful for surrogate models. So there's loads of examples in machine learning, like data modeling. I spoke with Andrew Ilias, or even Lime, and indeed your work as well. You create a very basic linear kind of data model, I think is a good way of describing it, where you learn a bunch of parameters and like a bias term in respect of an input example and your data set, if I understand correctly.
Yeah, so I think generally, the idea of using a surrogate model that is using a simpler model to understand the behavior of a more complex model is a very powerful idea. And in our case, we use the simpler model, we use a linear model to we assume that kind of the logits of this big LLM are a linear function in this kind of abstract representation space, which is highly nonlinear in the inputs. But kind of treating this abstract representation space fixed So treating all these embeddings as fixed, and then just treating kind of your final head that's producing the logits, which in the end, after you push them through the softmax, the next token probabilities, just treating that as a linear function now allows you to analyze it as a human, right? Now things become tractable, and that's very important if you want to make sequential decisions and want to optimize an objective. So that's why these surrogate models are so powerful. You're right in saying that in other domains, people have also looked at these surrogate models and also found them to be very powerful. So for example, kind of data models where you want to kind of learn how kind of certain data influences a certain prediction, or in Lime where you want to kind of fit a linear model that is actually interpretable, so not in some abstract representation space, but in a space that you actually understand. So then when you have trained this linear model locally for your prediction, you can look at that linear model and interpret the importance of the weights, right? Because you know this weight that is ascribed to a certain input has this specific meaning.
Isn't that crazy? So as you say, like these are highly nonlinear models, and I guess Lime is a kind of influence function where you have a linear model to kind of tell you what the weighting of the component features were for a given input example to make that prediction. And you gave the example of data modeling. It seems crazy to me that you could have a simple linear interpretable surrogate model.
So I think it's really a wider spectrum. So with Line, the reason it works is actually fundamental to the reason why local learning works, is because if you want to make kind of predictions that generalize across this entire data manifold, you need a very nonlinear function. Versus if you just want to explain one local prediction, kind of the hypothesis is that you can get away with a linear model because you need to encode much less information, right? You need a much less complex model. Your representation capacity doesn't have to be as big to explain this one prediction. Now, there's of course some limits to it, and in some cases it doesn't work so well. And Lime will tell you, okay, now we found this linear model, but the linear model doesn't actually track so well what the big model did. So that's kind of Lime. In the data models case, or in our case, we don't use that linear model to make predictions, right? And also we train that linear model in this nonlinear representation space. So essentially, I think fundamentally you can think about virtually any neural network as a big encoder, right? Until the penultimate layer. And then like one kind of linear, one final linear layer that projects to your output dimension. And in that way, that kind of neural networks are just sequences of linear functions that are composed with non-linearities.
Yeah, this makes a lot of sense. So yeah, Lime is short for locally interpretable model agnostic explanation. So for a given input example, in that local area, you can have a linear model. I guess it's the same thing with data modeling. You're basically saying for this input example, what's the influence of the data set. And actually, even MLPs are the same thing. So in spline theory of neural networks, it's saying that, models are locally affine. So for a given input example, you can actually represent the behavior of the neural network with a simple affine transformation, which is represented by the kind of like the cutout honeycomb space. So yeah, it's like, that's how deep learning models work. Essentially, they're just like, a massive confection of like linear transformations for a given input example.
Exactly. You're trying to essentially move to some space, like move data into some kind of space where it is represented in such a way that you can make predictions as linear functions. And that can be very powerful in the sense of actually designing your model, your representations, but also your functions in such a way that they will make good predictions, right? Because you know the structure.
Yeah, love it.
So data models, I think, people have also tried to use them to select data, but kind of a fundamental assumption or kind of some limitation that people have found is that if you kind of use these kind of linear models to learn how a certain kind of selected subset affects your test loss, let's say, or your prediction, then it implicitly assumes that the influence of data adds up linearly. And this is kind of So there's this, in interpretability, this big line of work on influence functions, and maybe we should explain what that is. So essentially, influence functions try to estimate the loss on a test point that you would have had if you had changed your model slightly, or if you had trained your model on that certain data point. So you can use it to understand that, this data point that I have in my data set influenced that loss kind of on this prediction to that degree, right? You can ask these kind of counterfactual questions. That's where it attempts to be helpful. Now, a problem is this is hard to make tractable, of course, and one kind of assumption that people typically do is they use a first-order Taylor approximation of the loss to get this working, or with data models. In a similar way, people use kind of first-order methods, and what that does, it ignores the mutual dependence of data relative to your prediction. So it just looks at the singular individual importance of one data point about a prediction. But of course, you train your model not on just one data point. You train your model on multiple data points. Yeah. And how you compose your training set is very important, not just in terms of what is the data you give, but also what is the data that you showed relative to the other data it has already seen. And in that sense, these methods are, when you use them for data selection, you just end up with something like nearest neighbor. You are going to do some nearest neighbor retrieval in some embedding space. But as we discussed, this nearest neighbor retrieval will completely ignore the fact that you can end up with completely redundant information. That if you show repeatedly the same example to the model, it will think that it improves because it will think that every example has the same value, but in fact it doesn't. And the marginal gain that you get from each example quickly diminishes.
This is really interesting. So you're saying that actually there are these first and second and maybe further order interactions between the data examples. We shouldn't think of them as being separate. And this reminds me of the ML security literature, so there's like data poisoning, for example, and that says that you can manipulate just the order of the data that gets trained on a machine learning model, and you can manipulate the model to do anything. You can even put backdoors in the model. So we need to have a method of sort of understanding the interactions between the data examples as well as the data examples on their own.
Exactly. I think that is really critical, and you see it empirically, and I mean also we see it day to day in our life, how we operate, right? So the decisions of the information we access today will influence what we find interesting tomorrow. Yeah. And this doesn't happen independently, right? We don't start every day independently from scratch and just sample a new point from this data distribution. We think about, okay, now I have kind of knowledge in this field and maybe there's some field in between that kind of would combine this knowledge, and now I would kind of sample knowledge from the third field as opposed to one of the first two because I already know these quite well.
So the $1 million question is, how do you do retrieval taking into account the interactions between the data points?
This is actually quite straightforward. So what we do is we build a simple, tractable surrogate model over which you can estimate the uncertainty that model has relative to making a certain prediction. So you get some kind of tractable quantity that describes how good your prediction would be if you would have shown the model a certain kind of set of data points. And that quantity can be optimized. So in closed form, you can minimize the uncertainty that this model has relative to making a certain response. And it turns out that this borrows really important ideas from nearest neighbor retrieval. So in particular, the first example that you take will be the nearest neighbor. But as soon as you look for the second example, you will try to find examples that are kind of as aligned as possible with your task in this latent space where kind of similarity is encoded kind of in this linear way. And at the same time, try to find examples that are as orthogonal as possible to the pieces of information that you have already accumulated.
So we'll get to the closed form solution in a minute because there's some beautiful mathematics around that. But just stating it just as an objective function, what are you actually trying to do?
So fundamentally, you can think about it from multiple different perspectives, but fundamentally you're trying to minimize some intrinsic objective of this kind of machine, of the LLM, which is to this uncertainty about making a good prediction. So we come up with some measure of uncertainty that describes how good the prediction will be, and then the machine tries to go out in its memory and find the relevant data that makes it end up with a good prediction. And you can frame this in multiple ways. I think I like really a framing that is more of a probabilistic, kind of from a probabilistic standpoint, where you think about your LLM as having epistemic beliefs about what could be the right function to describe your prediction. And you're slowly, kind of by showing it more data, you're manipulating these the machine is changing its epistemic beliefs through Bayesian updates, through probabilistic updates. So it's computing posterior epistemic beliefs. And now what kind of this objective is saying is it's saying the LLM should take those examples from memory that lead to the most certain posterior beliefs relative to the prediction that it's trying to make.
Okay, so what does certainty mean? Does that mean you're trying to sort of like minimize the variance of the posterior?
Exactly. So so of course, when you are working kind of in this probabilistic model framework, a key aspect is making that tractable. So that's kind of one of the key limitations of Bayesian inference, of probabilistic inference, is that computing this posterior is in general a very hard problem. But using this linear surrogate model and essentially Gaussian, treating the initial random variables as Gaussian and using a Gaussian observation model, this posterior update is tractable, so you can compute it in closed form. And then you have kind of this big distribution over kind of possible predictions that the model can make. And there's one prediction that you care about, right? So you are trying to minimize kind of some measure of uncertainty relative to that prediction. And for Gaussians, that's usually the variance. So you just minimize the variance of your kind of the epistemic variance of your model relative to the prediction that you're making.
So this is really exciting, right? Because I love Bayesian analysis. And unfortunately, we don't have access to a hypercomputer that can do all of the computations in the universe. So neural networks, they just produce bare predictions. They're like maximum likelihood estimators. They say this is the thing that's most likely. We don't have the kind of the confidence intervals. We don't have like all of the uncertainty that we had with the Bayesian method. So what you're saying is we have a linear surrogate model, and in that linear surrogate model, we can model the uncertainty. We can do confidence estimates and so on. And then the other thing is you can use kernels for this and Gaussian processes.
Well, in some degree, yes. I think the simplest form with this linear surrogate model is just Bayesian linear regression. So this is like the first Bayesian model that you are introduced to when you start working kind of with Bayesian machine learning, which is just kind of your kind of standard linear regression. But on top of that, you have a Gaussian prior over the weights, and then you have a Gaussian likelihood. So you have kind of an observation model that says that whatever observation you get is really the ground truth function plus some Gaussian noise that is IID. And in that framework, you can do this posterior Bayesian inference exactly in closed form. So you can write down the closed form solution to this. And this is fundamentally what we use when we use a linear surrogate model, is we kind of approximate this very complicated neural network by kind of a Bayesian linear regression, which is, right, it is a bad approximation in terms of making good predictions, but it turns out to be a good enough prediction relative to deciding, okay, what information is relevant to improving the prediction of the LLM.
And can you explain how it's possible to do that in closed form? Because, obviously you think of Bayesian analysis as needing to do complex solving and Markov chain Monte Carlo and all this kind of stuff, but you can just do it as a simple. I mean, maybe you should explain what I mean by closed form.
Yeah. So what we mean by closed form is generally that we can describe the probability distribution, the posterior probability distribution over weights, as a mathematical formula. And that can be derived directly from the formulas for the prior and the likelihood. So the way standard kind of Bayesian inference works, Bayes rule, is that you kind of compute your posterior probability as being proportional to the likelihood of your data times the prior, divided by some kind of term that normalizes this to be a true probability distribution. And the beauty is that if you do this with Gaussians, if you use a Gaussian prior and a Gaussian likelihood, then this kind of probability distribution will still be a Gaussian. That is fundamentally because kind of these Gaussians only have kind of these first order and second order terms, and they're kind of the one probability distribution that if you have this second order and first order term, you know you are with a Gaussian. And that's why you can do this in closed form.
Very cool. So we have described how we have a way of estimating the confidence for a given prediction. Now, what we want to do is use as much inference time computation as is required. Because if you think about it, we could just use like an unbounded amount. Well, that's not very good. Wouldn't it be cool if we could link the amount of inference time computation to the confidence estimate?
Yeah, absolutely. And we looked at this a little bit kind of in a recent preprint, because you can think about this as being kind of a powerful tool when we have kind of knowledge of how uncertain our model would be if it had seen certain data. And then we can think about, okay, how much do we actually want to pay in terms of how much compute do we want to pay to get a certain improvement in our model? So in that sense, we can use these kind of projections of how uncertain our model will be to stop computation early when our kind of uncertainty reduction stops being proportional to the amount of compute that we're paying. So usually for any type of prediction, you get this kind of submodular kind of curve where the marginal gains are diminishing over time because you're slowly accumulating information, and at some point you will have accumulated all the information that is required.
What do you mean by use intuition of LLM to make search tractable?
So, I mean, I like to think about this framework as having like this controller and this memory, right? And essentially what kind of maybe in like the standard computational framework, people think about the same two components, for example, with Turing machines. So you have this head, right, which is a finite automaton. And then you have this memory, which is this unbounded tape. Now, what we can do today, which is quite amazing with these learned abstract representations, is that we can essentially jump to any kind of piece of content that is stored in this memory, just using kind of the intuition or the abstractions that we have learned. Whereas kind of in the standard computational framework, you would have to move left and right on the tape of the Turing machine. Now, essentially in kind of log linear time, we can access the entire memory at once, or the relevant bits at least. So, and the controller has two important functions here in this framework. The first one, as I said, is being able to decide what pieces of memory it should operate on. And it can do so by leveraging these abstractions and representations to essentially move in this memory space, kind of using shortcuts instead of going left to right. And the second key component of this controller is that it learns representations and abstractions that allow it to ingest information from the memory. So it reads from the memory and then updates its weights, if you think about it in terms of a neural network. And we want kind of a controller that is very good at making these gradient step updates, right? So you can think about kind of better models, stronger models in this framework, stronger controllers as being kind of more robust to certain types of information it would read from its memory, and kind of leveraging its abstractions, leveraging its knowledge to actually use that information to make good predictions, right? It's like, I think a good analogy is that if you give a kid, some complex math textbook, it will probably not learn too much from it immediately because the representations and abstractions to make sense of that information are not there. So what we want with a strong controller is that whatever piece of information it fetches from its memory, it's able to interpret that and kind of use the information to its full potential relative to making a good prediction.
Yes. So the FSA is the controller, and then the two push down, stacks essentially are the memory.
Exactly.
But this is interesting, right? Because, LLMs are FSAs. So they just represent and Keith Duggar, my co-host, he's big on like Turing machines, and he always says that, you know, there is a class of algorithms which could run on a finite state automata, but, you know, act as a controller for a Turing machine. Yeah. And that class of algorithms, even though they could in principle run on an LLM, they're not traversable via stochastic gradient descent, because of course this is a thing with a fixed amount of memory. It can't expand its memory. But the broader point though is that the Turing machine class of computation can do essentially any type of computation. Yeah. And we're not just talking about an improved method here to improve predictive performance, you know, through specificity. We're actually talking about a new paradigm of Turing complete computation.
Absolutely. In a sense, you can think about this memory as potentially being unbounded and getting rid of this kind of limitation that pre-trained LLMs have, that they have to compress all the information at once into this kind of limited format that you cannot extend afterwards, that is kind of there. And if you want to come up with something different, you have to retrain from scratch, basically. And now you can augment that controller that has learned these kind of strong intuitions, strong representations that allows it to quickly kind of adapt to new information. You can use that in conjunction with this potentially unbounded memory, which kind of as you evolve that system over time, you can extend or add pieces, remove pieces of information as you please.
Yes. So it's a much more powerful modality of computation, but it's not something which is trained end to end with stochastic gradient descent. So we learn the memory, and then we handcraft the controller. And I guess it's a tiny bit janky because, like, you know, we have a fixed embedding space and we like retrieve from a certain data space and so on. Let's use the ARC challenge as an example. So the guys who are the winners of the ARC challenge, good friends of ours, the Minds AI team, they're doing test time, like transductive, active fine tuning. That's what they're doing. And how general is it, right? So what they're doing is they're saying, okay, well, we know what the priors are. We can build a data set generator. And then when an input example comes in, we can kind of like lean into that example and we can generate data and we can fine tune the language model. And then we've got a Python verifier. So it is kind of Turing complete, but it seems like it doesn't seem general. It still seems ARC specific, but it's certainly significantly more powerful than any other architecture, you know, that we know about so far. So we're kind of moving in that direction a little bit.
I think if you think long term about where I think the trajectory of these types of architectures is headed, I don't really see so many kind of fundamental limitations. Whereas in the current implementations, there are definitely a lot of fundamental limitations, as you said. So these are kind of representations which are learned once, kind of the controller is learned once and then kept fixed. Ideally, what you want is systems that learn over time, open-ended systems that learn from their mistakes and improve their representations and improve kind of the ability of the controller to ingest new information, adapt to a certain task over time. And certainly that is what truly intelligent systems do and what we don't really have at large scale right now. So that granted, I would say that if you scale this up as a system that has kind of this, if you will, kind of finite working memory that is kind of part of that controller and that can add to its memory and remove from its memory and doing so efficiently finding relevant pieces in its memory, I think kind of philosophically speaking, that is like a general mode of computation that can be quite powerful.
Will it always be specialized, though? I guess it comes to the philosophy of knowledge. So Francois Chollet thinks that there are primitives of knowledge. And if you have some kind of like, you know, set of primitives that you bias into the model, then you could in principle deal with any form of novelty. But any system that does retrieval, presumably it still needs to, there still needs to be some kind of manifold or some sketch of a future situation, which we could then lean into.
Absolutely. I mean, to the degree that any intelligent system constantly learns from its environment and learns kind of what is actually kind of what are the right abstractions to make good predictions in that environment, any intelligent machine has to do the same. So in whatever environment we put it, and if we keep the environment static, that's kind of what we're doing now, then that is a much simpler task. Kind of in whatever environment we put the machine has to figure out what are the kind of right abstractions so that it's able to find pieces of information and then combine these pieces of information to make good decisions. And I think there's nothing like in this paradigm, there's no fundamental limitation that you cannot do this in an open-ended system, but it certainly has not been done yet, and that's a super exciting direction.
So another thing that springs to mind is, I'm excited about active inference, and maybe in the future we'll have a very distributed asynchronous nexus of agents that are like, doing something very similar to what you're describing. So very situated active inference. And what you're describing right now is we have a monolithic language model which is updated every 6 months, and then we have some kind of like information retrieval store which is periodically updated, and at the point of doing prediction we basically do inference, right? And then I think we throw it away afterwards.
Exactly.
So then we can get into this federated paradigm where rather than throwing it away, we kind of like remember it. And initially we remember it just for me, but maybe I start sharing it with you, and maybe eventually it goes back to the mothership.
Well, we could remember the prediction. What we could also do is just remember the error in prediction, right? So whenever, and that's I think what a truly learning system does, is at test time, it does some additional computation, and then eventually it sees, okay, to what degree was that computation useful, fruitful, to what degree did I end up with a good prediction? And then it can kind of change the learning mechanism, right? You can update based on that prediction. You can change what you do next.
And would the cash value of that be like just updating the manifold in the original model? Or, there's this kind of MIT approach, like the dream coder type approach where you do some kind of abstract library learning. Like, do you think there's some way of introspecting useful abstract knowledge, or do you think it should just go back into the original neural network?
I think there are multiple ways to go about this. So I think certainly what you definitely want to do is you want to improve your representations and abstractions over time. But fundamentally, I see those as kind of strong intuitions that allow you to kind of fetch the right piece of information and then combine these pieces of information to come up with a strong prediction. And for those, these abstractions are necessary. Of course, what you also do, and I think pretty evidently what we also do as humans, is we continuously store patterns to our memory that we encounter at varying kind of degrees of fidelity. And, a machine can probably, if you give it sufficient memory, store these patterns at much higher fidelity than a human could ever do. So I think both storing information and updating kind of your representations to account for the fact that your environment is changing and the amount or the types of information that you're dealing with are changing are both key aspects to getting a really truly intelligent system.
Yeah. Do you think, the O1 model does and by the way, maybe we should talk about this concept of a scaling, like a inference time scaling law that they introduced, but do you think they do something like this? Do you think that they estimate their confidence or knowledge and then they do a variable amount of computation, or do you think it's still like quite basic?
It's really hard to comment on what OpenAI does or does not do with O1, because unfortunately we really don't know much about what they're doing internally. All that they're saying is that they are spending some amount of compute at test time to kind of change their model, or at least kind of work their model around to end up with a different prediction than they would have otherwise ended up with if they just did kind of one forward pass through the model. And to that degree, I think it is kind of related, and it's part of this paradigm of kind of spending computation locally, kind of changing the resolution locally, kind of the accessible resolution locally around prediction that we're working on. But I don't think that they are necessarily kind of doing this in this kind of intrinsic uncertainty minimization framework of kind of that is related to active inference or these types of things, because I haven't seen them talk about this.
Yeah, but they kind of should be, and that's the thing. So when you use language models all the time, you get a feel for them, and you can feel when they go out of distribution. And because what's actually happening is when you lean in, when you ask it about something where it's like, it's on a well-sampled, dense part of the manifold, you get rich answers. But that manifold is actually, it's like a landscape. And sometimes you're in no man's land, and it just gives you the most banal, like almost nonsensical answers. And wouldn't it be cool if it knew that?
Yes. So I think now we're really touching a very important point, and that is can we tell whether we kind of have information that is relevant to making a good prediction or not? And that's actually some kind of piece of information that we can extract from these uncertainty estimates. So kind of getting a handle on our uncertainty about making a prediction can be very useful to tell, is kind of the information that is stored in memory, can that be useful given my current abstractions and this task that I'm faced with to actually solve that task? Or is it not useful? In the Michael Jordan example, if the age of Michael Jordan and his kids are not actually stored in memory, then and also not in your weights, then there's no way to make a good prediction. There's no way to produce a good output. And we actually discussed to some degree that you can use these kind of uncertainty estimates to kind of provide an insight as to what your model is capable of doing and what your model is not capable of doing. And one of the key aspects where this shows up is actually in proving convergence guarantees. So one of the cool things that you can do is if you're minimizing, if you're taking this principled approach of selecting the most informative data or selecting the data that maximally reduces your model's uncertainty, your model's epistemic uncertainty, then you can show that relative to the data that is available and relative to how good your model's abstractions are, eventually you will kind of make the best possible prediction. Eventually your uncertainty will shrink to be as small as possible. And that is something that is not possible if you select data using nearest neighbor search. But going back to the other point that you made relative to, do we in these dense parts of the data manifold, do we actually have models that are as good as they can be? And I wouldn't be so confident about that. Right? Clearly, in those kind of very sparse parts of the data manifold we have where the model hasn't seen much data, it's not good, and we realize that today. But I think a fundamental problem is kind of in this inductive paradigm when you're pre-training the models to be good everywhere. Clearly, in the parts that are most well represented in your training distribution, it kind of, if it weren't doing well there, its loss will be very high. So and it kind of is trained to be very good there. But still, if you kind of zoom in to these parts, with whatever kind of representational capacity you have, you can still represent them in a kind of at higher fidelity.
I guess like one thing I was asking earlier, but maybe I don't think I asked it in a very good way, is right now we've got this modality where it's two extremes. So we've got the most general possible thing, which is the induction, and then we've got the most specific possible thing, which is the transduction. And could there be a middle way? Like, for example, could you have a kind of pyramid scheme where you do the most specific thing, but you also kind of like have an ensemble of varying levels of like coarseness? Could that be better?
I think to some degree this is happening already. So if you look at how models are trained today, models are trained by first kind of in the pre-training phase, just fitting kind of this big mass of human generated data. And you try to give to it as much data as possible. But then people realize, okay, I don't actually care about kind of specific data that I find on the internet in some obscure forum. What I actually care about is maybe math or is coding. And then what people do is they curate kind of data that is very specific to that part of the data manifold, and they fine-tune the model on that. And you can think about that as some amortized form of transductive learning. And actually, I like to think about transductive learning as kind of this entire spectrum all the way. So there's a special case of transductive learning, which is inductive learning, where it's really you care about the entire data manifold. And then there are all these kind of cases where you care about some subparts of the data manifold. So you kind of carve it up into the actual region that you find interesting for the task that you're trying to solve. But still, you train your model once, and then you freeze it, and then you deploy it, but just on that subpart of the data manifold. And what local learning is doing is it's really going to the extreme end of that. It's pushing it to the extreme and saying that whenever you use one of these language models, let's say, you are always interested in just making one prediction. So you might as well train a specific model just for that one prediction, and for the next prediction, you can again train a specific model.
Yeah, I mean, first of all, it's quite interesting that we're almost going back to where we started, which, I mean, Google search is really good, and that's pure information retrieval. And then we kind of went 180 and we did pure, inductive inference. And now we're kind of like meeting in the middle. But I think it has the potential to solve a lot of the kind of the failure modes and problems that we have, like when I'm doing generative coding or something like that. The problem is always situations where you're dealing with ambiguity. And yeah, you can do a lot with prompt engineering. You can say, no, I meant this, no, I meant that. But I think there's a lot of that kind of ambiguity resolution could be automated by having some kind of like somewhere on that transductive spectrum.
Yeah, I think in practice, when we spend compute at pre-training time, usually, and this is kind of what people today do with scaling laws, is they say, okay, I'm able to spend this amount of compute. And then the scaling laws tell you I'm able to train a model of that certain size, right? But of course, if you had more compute, what you would want is you would train a bigger model, right, on more data. And instead of just training bigger models, what you can do is also to increase your representational capacity, or at least your effective representational capacity relative to making a certain prediction, is not to just increase the kind of model size, but instead is to use that model size in a smarter way, right? Instead of just using that model size to kind of trying to solve all problems at once, you can use that model size, but using kind of essentially duplicating that model, training a separate model for every prediction. Now, you don't have to train a separate model from scratch, and that certainly would be very inefficient. So instead, what you can do is you can train a model that is amortized, that is still trying to solve all problems at once, at least to the degree that it's capable of with its representational capacity and with the amount of compute you give it. And then kind of leverage that as an initialization to learn a specific model where then all of the representational capacity is available to fit the information or compress the information that you need to make a certain prediction.
So let's talk about how this might pan out practically. So I don't think these huge language models are going away anytime soon, right? So, we're going to have the Sonnet 3.5s for doing coding and so on. But I see a future where interesting things might start happening. So, for example, laptops are getting ridiculously fast now. I've just ordered the new M4 MacBook Pro. Oh, it's going to be amazing. And that could, in principle, fine-tune a Llama model as I'm going. So, like I'm on my repo, it fine-tunes it on the repo. And I can imagine there being some kind of a hybrid thing where, like, we get the small model doing the active fine-tuning, and then we kind of generate a completion with that, and then maybe we sanity check it back over with Claude, and then we do some information retrieval. Do you see some kind of, like, practical hybrid use case of this coming up?
I think that is certainly possible. I think what seems certainly interesting is that with a model that is smaller and that kind of compresses kind of more of this abstract information into a smaller package, it's easy to do to learn at test time with such a model, just because backprop through that model, but also forward pass it through that model. So leveraging that intuition to search things is much easier. Nevertheless, what we have seen is that at all scales, kind of learning at test time can improve performance. So even if you kind of work with kind of more state-of-the-art models, still doing this local learning at test time improves performance. So what I estimate is that where you spend compute and how much compute you spend will in future be very dependent on the certain problem, on the concrete problem that you're facing. Because there's certainly some amount of fixed compute that you will have on your machine, but I believe that also these kind of providers that kind of provide these big LLMs over cloud services will over time move to a setting where they allow variable amounts of inference time compute, and you can essentially tell how much compute do I want to spend on the certain problem. So there might be a very nasty kind of research problem that you want to offload to an LLM in the future, and which seems kind of obvious to you, but like a lot of redundant work. And I believe in the future, you will just be able to tell it, okay, use whatever kind of compute is necessary to solve that at test time. And that might be more expensive than what your local computer can handle. But I think we will see this expansion of compute in two scales. We will see it, one, just leveraging the compute that is available in our machines that would otherwise be unused, right? But I think we will also start paying, so like actually acquiring additional compute that would otherwise be used for something else, for, let's say, pre-training. We will start paying for this additional compute to solve more complex problems. Just because we have seen that at all scales, you can kind of get better performance if you spend this additional compute.
Yes, and it also fixes the fundamental problems with the monolithic paradigm, which is that right now it's not open-ended, right? And when we actually do have this ability for people to explore different parts of the landscape, and then we can kind of take those lessons back to the collective, we've now got a divergent creative AI system as a whole, which is great. But Jonas, this has been amazing. So first of all, I'm really excited about your work, and it's great that you're telling the audience about it, because first of all, I think uncertainty and confidence estimation is really important. So I hope people have learned about that. I think intelligence is about being able to do a commensurate amount of computation based on your uncertainty. That's really important. And I think that transductive active fine-tuning is going to be absolutely huge over the next 5 years. So thank you very much for joining us today. It's been amazing.
Thank you so much for having me on. I'm really excited about this.